You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Application Programming Interface Security is one of the most important areas of cloud application defense because APIs form the backbone of modern software architectures. The purpose of API security is to apply layered protections that authenticate identities, enforce access control, and regulate traffic so that services remain both functional and resilient. APIs expose critical business logic directly to consumers, partners, and internal services, making them attractive targets for adversaries. A compromise in API security can lead to data leakage, privilege escalation, or denial of service at scale. For learners, understanding API security means appreciating how each layer identity, access, validation, and rate control works together to ensure that APIs remain trustworthy under constant scrutiny. Without these defenses, even well-designed systems can be undermined by a single weak endpoint. APIs come in several styles, each with distinct security considerations. REST APIs, widely used due to their simplicity and alignment with HTTP semantics, must guard against injection, weak authentication, and improper object-level authorization. Remote procedure call protocols such as gRPC use binary formats and strong contracts, but still require controls on identity and transport encryption. WebSocket APIs enable real-time communication but expand the attack surface by maintaining long-lived connections that must be secured against hijacking or abuse. Each type brings its own trade-offs, but all require authentication, authorization, and input validation. By tailoring security practices to the API style, organizations ensure that protections match protocol characteristics rather than applying one-size-fits-all assumptions. Specification documents provide the foundation for governing API behavior. Standards such as OpenAPI define paths, methods, schemas, and expected responses in machine-readable form. These specifications allow validation tools to confirm that requests match allowed inputs, reducing the risk of injection or deserialization flaws. For example, an OpenAPI schema may specify that an endpoint accepts only integers within a defined range, preventing malformed or malicious payloads. Specifications also serve as documentation for developers and as enforcement points for gateways and testing frameworks. By treating specifications as contracts, teams embed security into design and implementation, ensuring that endpoints behave consistently and predictably. Authentication establishes the caller's identity and forms the first gate of API protection. Modern APIs rely on standards such as OAuth 2.0, OpenID Connect, and Mutual TLS to prove identity. OAuth tokens allow users and applications to authenticate without sharing credentials directly, while OIDC extends this to provide federated identity across providers. Mutual TLS strengthens service-to-service authentication by requiring both sides to present trusted certificates. For example, a payment gateway API may require OAuth tokens for users and MTLS certificates for internal service calls. Without strong authentication, APIs cannot enforce meaningful access controls, leaving endpoints open to abuse. Authorization enforces least privilege once identity is established. Mechanisms include scopes for narrowing access to specific functions, roles for grouping permissions, attributes for dynamic context checks, and resource-level restrictions for fine granularity. For instance, a token with the read profile scope may allow reading but not modifying user data. Attribute checks might restrict data export to trusted device classes. Authorization ensures that even valid identities are constrained to their intended actions, preventing privilege escalation. In cloud APIs, where resources are granular and sensitive, precise authorization is critical to protecting both data and system integrity. Token formats standardize how identity and authorization information is conveyed. JSON Web Tokens, or JWTs, are widely used, carrying signed claims about the subject, scope, and expiration. Because JWTs are signed, consumers can verify integrity without contacting the issuer, making them efficient at scale. For example, a JWT may carry a claim limiting access to a specific project, with expiration set to 15 minutes. Proper use of JWTs ensures tokens are verifiable, time-bound, and context-aware. Improper use, such as failing to validate signatures or allowing excessive lifetimes, undermines their value. Proof key for code exchange strengthens OAuth 2.0 authorization code flows, particularly for public clients that cannot safely store secrets. PKCE introduces dynamically generated codes that prevent interception attacks, ensuring that even if an authorization code is stolen, it cannot be exchanged without the associated proof. For example, a mobile application may use PKCE to secure its OAuth flows. This enhancement reflects the principle of adapting authentication protocols to real-world threat models, particularly for environments where secrets cannot be safeguarded. The client credentials flow enables server-to-server access, providing narrowly scoped tokens with bounded lifetimes. This flow avoids interactive login, allowing backend systems to authenticate directly to APIs. For example, a microservice retrieving metrics from a monitoring API might use the client credentials flow. Tokens are issued for short durations, ensuring that compromise windows remain small. By scoping and expiring these tokens, systems balance automation with security, ensuring that machine-to-machine calls remain governed and auditable. API keys provide simple identification for clients, but must be treated as secrets. Keys should be rotated regularly, scoped to specific resources, and rate-limited to reduce risk. For example, a key used by a trusted partner may be valid only for a specific API set and expire after 30 days. Keys are easy to implement but dangerous if mishandled, as they often lack the contextual claims of tokens. Treating keys with the same rigor as passwords or certificates is essential, preventing them from becoming weak links in API ecosystems. Input validation is a cornerstone of API defense. Enforcing schema, type, size, and encoding constraints prevents injection, buffer overflows, and deserialization attacks. For example, a field defined as an email address should be validated for format and length before processing. Validation ensures that only well-formed data enters the application, reducing the attack surface dramatically. Without it, APIs become vulnerable to adversarial payloads that exploit weak parsers or logic. Combined with output encoding, input validation protects both services and users from corrupted flows. Cross-origin resource sharing policies regulate how browsers can request data from APIs. CORS rules must restrict origins to trusted domains and limit methods and headers to what is necessary. Overly permissive settings, such as allowing all origins, expose APIs to cross-site request forgery and data leakage. For instance, a healthcare API should allow requests only from the official application domain. Properly configured CORS reflects the principle of minimizing exposure, ensuring that only intended contexts can interact with APIs. Rate limiting is critical to maintaining availability. By constraining request frequency per identity, key, or IP address, rate limits prevent abuse from brute force attacks or accidental floods. For example, a login API may restrict attempts to 5 per minute per account. Quotas define sustained usage over longer intervals, while burst controls allow temporary spikes without overwhelming services. Together, these measures balance user experience with protection. Without rate limiting, even benign clients can unintentionally degrade systems. Idempotency keys ensure that repeated requests do not cause duplicate side effects. For example, if a payment API receives a retried request, the idempotency key ensures that the transaction is processed only once. This protects both systems and users from duplication caused by retries, replays, or network glitches. Idempotency reflects the principle that reliability and security overlap, preventing denial of service or financial harm from inadvertent repetition. Error handling must be disciplined, avoiding leakage of sensitive details such as stack traces or database queries. APIs should return consistent codes and generic messages that inform clients without aiding attackers. For example, returning 401 unauthorized is safer than exposing whether a username exists. Proper error handling preserves confidentiality while still supporting debugging through logs. It illustrates how small design choices can have large security implications. The OAuth API Security Top 10 provides a catalog of common risks. Issues such as broken object-level authorization, excessive data exposure, or lack of rate limiting appear repeatedly in real-world incidents. For example, broken object-level authorization occurs when APIs allow one user to query another's data simply by modifying an ID parameter. Familiarity with these categories ensures that developers and defenders focus on the most impactful risks. OWASP provides a practical lens for prioritizing controls, ensuring that defenses align with observed attack patterns. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. API gateways provide centralized enforcement points that integrate authentication, authorization, throttling, and observability. Instead of embedding controls in every service, gateways standardize protections across all inbound traffic. For example, an API gateway can validate OAuth tokens, enforce quotas, and log requests consistently before forwarding them to back-end services. Gateways simplify developer workloads while ensuring uniform policy enforcement. They also provide visibility, capturing telemetry about usage, latency, and error rates. In cloud-native environments with dozens of microservices, gateways serve as both control plane and visibility hub, making them indispensable for scalable API security. Web application firewalls add another layer by inspecting traffic for anomalies and common HTTP-based attacks. While gateways focus on identity and policy enforcement, WAFs detect malicious payloads such as SQL injection, cross-site scripting, or path traversal. For example, a WAF can block attempts to submit script tags in form fields or detect abnormal query patterns in URLs. Positioned alongside gateways, WAFs reduce risk by filtering out known attack signatures and abnormal behaviors. They complement specification-driven validation by catching threats that exploit parser quirks or unanticipated code paths. Together, gateways and WAFs provide a layered shield for APIs exposed to the Internet. Request signing with HMAC strengthens integrity by ensuring that API calls cannot be modified in transit without detection. Each request includes a signature generated with a shared secret and verified by the server. For example, financial APIs may require clients to sign each call with HMAC, proving authenticity and preventing tampering. This technique also protects against replay, as signatures often incorporate timestamps or nonces. Request signing is particularly valuable for sensitive operations such as fund transfers or contract approvals. By verifying both origin and integrity, HMAC adds a cryptographic guarantee on top of transport-level encryption. Mutual TLS elevates trust in service-to-service calls by requiring both client and server to authenticate with certificates. Unlike one-way TLS, where only the server is validated, MTLS ensures that services cannot impersonate one another. For example, in a service mesh, each microservice may present a short-lived certificate issued by the mesh's certificate authority. This prevents unauthorized services from joining communication flows. MTLS enforces strong identity assurance while still providing encryption in transit. It aligns well with zero-trust principles, making every service prove itself before exchanging data. Secrets management remains essential for API security, ensuring that keys and tokens are never hard-coded or left unmanaged. Vaults and cloud-native key management services provide runtime injection of credentials, encrypted storage, and audit trails for retrieval. For example, An API key for a third-party payment provider may be fetched at runtime from a vault, used briefly, and discarded. Automated rotation further reduces exposure windows. Secrets management integrates directly with CI/CD pipelines and gateways, embedding governance into the lifecycle. Without it, credentials often sprawl across code and configuration, creating silent liabilities. Pagination and result limits defend APIs against resource exhaustion. Unbounded queries or massive responses can overwhelm databases, memory, or bandwidth. By enforcing page sizes and maximum results, APIs preserve availability while still serving client needs. For example, a query for customer records may return 50 results per page, with explicit limits on maximum pages. Attackers attempting to exfiltrate large datasets are constrained, while legitimate users receive predictable performance. Pagination reflects the principle that APIs must guard against both intentional and accidental overloads, embedding resilience directly into endpoint design. Caching strategies improve performance but must respect authorization contexts. Improper caching can lead to data leaks when responses intended for one user are served to another. To prevent this, caches should vary responses by authorization tokens, headers, or parameters. For example, a content API may cache results for anonymous queries, but bypass caching for authenticated, user-specific data. By designing cache policies carefully, systems achieve efficiency without sacrificing confidentiality. Security-conscious caching treats authorization as a dimension of uniqueness, ensuring that sensitive data is never inadvertently exposed. Versioning and deprecation policies manage change while preserving security guarantees. As APIs evolve, older versions may contain vulnerabilities or lack modern protections. Versioning ensures that clients can migrate gracefully, while deprecation sets timelines for retiring insecure endpoints. For example, an API may release version 2 with stricter authorization, while version 1 remains supported for 6 months before deprecation. Governance ensures that no outdated, insecure versions linger indefinitely. Versioning transforms API evolution from a chaotic process into a structured one, aligning progress with ongoing assurance. Telemetry is vital for making API behavior observable. Gateways and services should emit request IDs, caller identities, response times, errors, and policy enforcement results. This telemetry supports detection of anomalies and forensic investigation. For example, linking request IDs across logs allows analysts to trace a suspicious transaction through every stage. Structured telemetry provides both operational insight and security evidence, ensuring that APIs are not black boxes but transparent systems. By embedding observability, API security becomes measurable and actionable. Anomaly detection builds on telemetry by flagging unusual usage patterns. Spikes in request rates, access to high-value objects, or invocation of rarely used methods may indicate abuse. For instance, a sudden surge of delete requests on an administrative API is a clear red flag. Automated anomaly detection enables proactive defense, alerting responders before full-blown exploitation occurs. Combined with rate limits and quotas, anomaly detection adds adaptive intelligence, catching behaviors that static policies cannot anticipate. Contract testing validates that implementations conform to specifications and security expectations. By testing actual API behavior against OpenAPI or gRPC definitions, contract tests ensure that endpoints do not accept unexpected inputs or produce dangerous outputs. For example, a contract test may verify that a required authentication header is enforced on every request. Contract testing reduces drift between specification and reality, ensuring that documented protections are implemented consistently. It also supports regression testing, catching when changes inadvertently weaken security. Fuzz testing pushes APIs further by submitting random or malformed inputs to uncover hidden weaknesses. Parsers and validators often fail under unexpected conditions, creating exploitable flaws. For example, fuzzing may reveal that a JSON parser crashes when fed deeply nested arrays, leading to denial of service. Fuzz testing explores the edges of input handling, surfacing vulnerabilities that structured test cases miss. By integrating fuzzing into pipelines, organizations discover weaknesses before adversaries do, strengthening robustness at scale. Egress controls are an often overlooked part of API security. API handlers must be constrained in what outbound connections they can initiate, preventing compromised services from becoming pivot points. For example, an API that processes user-submitted URLs may be restricted to fetch only from approved destinations, blocking SSRF attacks that target internal metadata endpoints. Logging all outbound calls ensures auditability. Egress controls complement inbound protections, acknowledging that compromised APIs may themselves be exploited as attackers. Tools. Compliance evidence packages tie API security to governance obligations. Specifications, gateway policies, token configurations, and logs provide proof of adherence to frameworks such as PCI-DSS or GDPR. For instance, evidence may demonstrate that only short-lived, scoped tokens are used for payment APIs and that rate limits enforce contractual SLAs. Packaging this evidence streamlines audits and reinforces accountability. Compliance integration shows that API security is not only technical but also regulatory, binding design choices to legal obligations. Anti-patterns highlight what weakens API security. Wildcard scopes grant excessive privileges, exposing data unnecessarily. Long-lived tokens extend compromise windows, undermining identity assurance. Failing to validate input leaves APIs open to injection. Unauthenticated administrative endpoints represent some of the most catastrophic missteps, granting attackers immediate control. Recognizing and avoiding these pitfalls is as important as adopting best practices. Anti-patterns serve as reminders that shortcuts in API design often become vulnerabilities in production. In summary, resilient API security unites strong authentication, precise authorization, validated inputs, and governed traffic controls. Gateways centralize enforcement, WAFs filter malicious payloads, and cryptographic signing preserves integrity. Secrets management, pagination, and caching policies prevent exposure and overload. Versioning and telemetry sustain security across evolution and operations. Fuzzing, anomaly detection, and contract testing validate robustness against adversarial and accidental misuse. Compliance evidence ensures accountability, while avoiding anti-patterns preserves discipline. Taken together, these practices make APIs not only functional but also auditable, resilient, and defensible in cloud-native ecosystems. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.